Hello there and welcome back to the Sleep Science channel, where we take impossibly huge questions and wrap them up into something you can drift off to. Tonight, it's the entire universe spread above your head, billions of galaxies stretching into distances your brain has no business trying to calculate this late at night. Imagine you're lying flat on your back, the grass cool beneath you, staring at a sky so clear the Milky Way smears across the black like a streak of spilled glitter. The stars feel infinite, but of course they're not. Somewhere out there is an edge, not a wall you could knock on, but a horizon beyond which light has never had time to reach us, and scientists, in their stubborn way, have now measured just how far that horizon stretches. Spoiler, you probably won't survive this math. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and I'd love to know where you're listening from. Drop your location and local time in the comments. There's something magical about knowing someone is hearing this while the sun rises halfway across the planet. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You start with your breath slowing, matching the steady hum around you, as if your lungs are syncing with the rotation of Earth itself. The grass shifts, insects buzz, and overhead the sky widens until you're not just looking at stars, you're inside a dome so deep your thoughts fall upward. If you've ever been out in the countryside far from street lamps, you'll know the shock of seeing more stars than you thought possible. They tangle in strands, crowd in clumps, and vanish into faint fog that centuries ago people thought was smoke or the breath of gods. It's easy to forget that the word universe once meant something much smaller. For your distant ancestors, the universe was just the dome overhead, sprinkled with lamps, with maybe some fire gods poking holes to peek through. Historians still argue whether ancient Mesopotamians truly believed the sky was solid, or whether it was more a poetic metaphor, but what's certain is that their world felt finite. They measured the heavens in cubits and days, not light years, and yet even without a telescope they tracked stars with precision. Imagine standing in Babylon around 500 BCE, priests charting Venus as it flickers low in the twilight, recording each appearance in clay tablets that still exist today. One quirky tidbit, the Babylonians weren't just stargazers, they were some of the first statisticians using planetary cycles to predict future positions like cosmic weather forecasts. Fast forward a few centuries and you find yourself wandering through Athens, where a fellow in a tunic named Aristarchus squints at the sky and dares to suggest the sun, not the Earth, sits at the centre. Nobody believes him. A couple of centuries later, Ptolemy builds a whole geometric contraption of circles within circles to explain planetary motion, because the idea of Earth spinning around the sun was frankly too weird to swallow. You can almost picture the philosophers debating under oil lamps, half serious, half dramatic, as though arguing over whether olives or figs are superior snacks. The takeaway here: humans have always wanted to measure the sky, even when their rulers of choice were bits of string and clever guesses. Now, stretch that curiosity across 2 millennia. Galileo finally lifts his telescope and gasps at moons orbiting Jupiter, at Saturn's mysterious ears — he didn't yet realize they were rings — at countless stars hidden in that smoky band called the Milky Way. For the first time you see depth, layers of stars upon stars. It's like zooming out in a video game and realizing the map is 10 times bigger than you thought. The universe starts to swell in human imagination, spilling past any finite dome. But here's the tricky part. Even Galileo, even Copernicus before him, still couldn't measure how far away those stars actually were. They knew the heavens were vast, but vast is not a number. It wasn't until the 19th century that astronomers finally cracked the first real unit of cosmic distance: stellar parallax. The trick works the same way your 2 eyes give you depth perception. Close one eye, hold up your finger, switch eyes, and watch your finger jump against the background. Now imagine doing that with Earth itself, snapping one photo in January, another 6 months later in July, and measuring how a nearby star shifts against the far background. The shift is minuscule, fractions of a degree smaller than your fingernail held at arm's length, but it lets scientists finally put numbers to the sky. The first star distance measured? 61. Cygni, about 11 light years away. Not exactly a tourist destination, but a revelation at the time. Of course, once you have a ruler, the temptation is to keep stretching it. Astronomers chased farther stars, then galaxies, building a cosmic ladder of methods. Each rung gave a little more reach, though always with some wobble of uncertainty. But hold that thought, we're not climbing the ladder just yet. For now, you lie in the grass and marvel that light itself is a messenger, racing for years, centuries, even billions of years to hit your eyes tonight. That twinkle you're staring at might be older than humanity itself. Here's the funny thing. If you were some ancient shepherd in the hills, you'd see the same stars. Sure, a few novas might flare and fade across the centuries, but the big patterns remain. Orion, the Big Dipper, Cassiopeia, all reliable companions across generations. They look permanent, but really they're just convenient illusions created by perspective. The stars of Orion are nowhere near each other in reality. They just line up neatly from Earth's angle. Historians still argue whether early civilizations knew this or whether they genuinely thought those constellations were carved and placed by gods. Either way, the permanence of the sky gave them comfort. And maybe that's the secret. Whether you're in 500 BCE or 235, the night sky always promises something bigger than your own little worries, and bigger it is. Tonight, scientists put numbers on that promise, and the numbers are absurd. The observable universe, the part from which light has had time to reach us, is about 93 billion light-years across. That's light, the fastest thing known, travelling for 93 billion years just to cross from one side to the other. Of course, the universe itself is only about 13.8 billion years old, which doesn't add up neatly, does it? That's where cosmic expansion comes in. While light travels, the fabric of space itself stretches, like trying to walk across a moving walkway that keeps extending ahead of you. What you see in the sky is not where things are now, but where they were when the light left them. It's like checking a friend's Instagram story from 7 years ago and assuming they still have the same haircut. So here you are, pinned under the weight of that number, feeling both tiny and infinite at once. 93 billion light-years, a figure so huge it doesn't even fit inside your imagination. And yet, here we are, daring to measure it anyway. You may not survive the math, but you'll survive the awe. And as your breath slows, stars blur into streaks, and you realize that measuring the universe is not about reaching its edge, but about learning where you fit inside its boundless glow. You're still stretched out beneath the stars, but now your mind starts tugging at the word horizon. On Earth, that's easy. The horizon is where your sight gets cut off by the curve of the planet. You stand on a beach, watch the line where sea and sky kiss, and that's it, that's all you can see. If you climb a hill, your horizon widens. Add a drone, wider still. So it makes sense to think of the universe as having a kind of horizon too, except instead of being blocked by terrain, you're limited by time itself. Light can only travel so far since the Big Bang. The edge of the cosmic horizon is not an obstruction, but a limit to what can physically reach you. The difference is, you can't hop onto a cosmic ladder to peek over. You're locked inside this bubble of light. That bubble has a radius of about 46 billion light-years in every direction, which when you double it, gives that 93 billion figure scientists like to flex at conferences. It's essentially the farthest distance light has managed to travel to us in the 13.8 billion years since everything kicked off. But here's the head twister. That doesn't mean the universe itself is 93 billion light-years wide. That's only the observable patch. The rest could be infinite, could curve back around like a cosmic Pac-Man map. Historians still argue whether Einstein himself leaned more toward a finite closed model, or if he left enough wiggle room to accommodate infinity. Picture yourself driving across a desert highway. Sand stretches as far as your eye can manage, but eventually haze makes it look like the world just dissolves. You know the land doesn't stop there, it just slips beyond your sight. The cosmic horizon is the same. It isn't an end, it's just the farthest your headlights, aka photons, can illuminate. And those photons are ancient. Some have been travelling longer than Earth has even existed, like little interstellar Uber rides showing up very late but still arriving. Here's a fun tidbit. The word horizon comes from the Greek horizon kyklos, meaning limiting circle. Aristotle used it to describe the edge of Earth's shadow on the sky. So when modern astrophysicists talk about the particle horizon or the event horizon, they're really borrowing ancient vocabulary to describe limits way beyond what Aristotle ever dreamed. If Aristotle heard, your observable horizon is 46 billion light-years, he'd probably spit out his olive oil. Of course. You might be thinking, if the universe is only 13.8 billion years old, shouldn't the horizon be 13.8 billion light-years away? Fair question. The universe is like bread dough rising in the oven. As light travels through space, the dough itself expands, stretching the distance. So while a photon might have only been travelling for 13.8 billion years, the space between you and its starting point has inflated into something much bigger. It's like mailing a letter to a friend across town only to find that, during its journey, the whole town was loaded onto a moving truck and hauled halfway across the country. And it's not just size, it's shape. Earth's horizon is curved because the planet is round. The cosmic horizon is curved too, but on a mind-melting scale. Current evidence suggests the universe is flat, at least to within a fraction of a percent, which is wild. A flat universe means parallel lines never meet. Geometry behaves as your high school teacher promised, and the cosmic horizon really does resemble an ever-expanding sphere around you. But here's the kicker. Every galaxy has its own horizon. To someone peering from Andromeda, the bubble of visibility would center on them, and it would look just as endless. Everyone gets their own cosmic snow globe. It's here that human imagination both triumphs and falters. Ancient myths imagined domes, shells, or curtains separating us from divine realms. You, lying in the grass, can still feel that same instinct, the need for an edge, something solid you could maybe tap on with your knuckles. Yet the universe resists that tidy closure. Scientists suspect there is no outer boundary. Instead, you're in a boundless expanse that only feels finite because your eyes and telescopes can't catch up with the speed of expansion. It's like sitting in the front row of a fireworks display. Sparks keep blooming farther than you can see. But you know the explosions don't just stop where your vision cuts off. A little joke to soften the vertigo. Technically, your observable horizon is shrinking every time you close your eyes. Those photons have been racing toward you for billions of years, and here you are, taking a nap. Somewhere in the Andromeda galaxy, an alien is probably doing the same, snoozing through cosmic history's greatest free light show. Back to the horizon, it isn't static. It evolves. As time passes, light from farther galaxies keeps reaching us, adding to the observable patch. But here's the tragic twist. Because of accelerating expansion, many galaxies are now receding faster than light itself can close the gap. That means some regions, once barely inside our horizon, are slipping permanently out of sight. The night sky of the far future will look emptier. The great clusters gone like ships sailing beyond reach. Your cosmic horizon is both a gift and a countdown. It's funny. Seafarers once thought sailing past the horizon meant falling off Earth. In a way, we've circled back to that anxiety. Only now, instead of wooden ships, it's photons carrying us to the edge, and instead of falling, we just stop seeing. Historians still argue whether early sailors truly believed in falling off or if that was just a medieval cartoon myth, but the metaphor sticks because it feels so human. You want the horizon to be a wall you can lean on, not an invisible fade into silence. So tonight, as you breathe under the stars, let your mind imagine that giant sphere around you, 46 billion light-years in radius, shimmering with ancient light. Not an end, just a limit of your view. Beyond it, the universe keeps stretching, galaxies keep spinning, stars keep exploding, but all of it forever beyond your reach. And somehow, that makes the part you can see even more precious, like a campfire circle in the dark. Your breath is steady now, in and out, almost matching the rhythm of the stars. The grass beneath you presses against your back, and as your gaze softens, your imagination drifts backward, long before telescopes, long before satellites, to the very first humans who dared to measure the sky. Picture yourself standing on a dusty plain in Mesopotamia, somewhere around 2000 BCE. The air is dry, a little gritty, and overhead the sky is crowded with pinpricks of light. You're not just looking up for beauty, you're looking up for survival. The stars are your calendar, your compass, your reminder of when floods might come or when crops must be sown. The Babylonians, masters of early astronomy, kept meticulous records of the heavens. They scratched the positions of stars, planets, and even eclipses into clay tablets with sharp reeds. Those tablets survive today, silent proof that 4,000 years ago someone else was standing in the night, squinting at Venus the same way you are now. One of their quirks? They treated planetary movements a bit like stock market data. By comparing cycles and predicting repeats, they could forecast celestial events with impressive accuracy. Imagine the prestige of being the village expert who can call an eclipse. It's like being the weather app of the Bronze Age. Historians still argue whether these forecasts were strictly scientific or wrapped in mysticism. but the line between priest and scientist was thinner back then, often blurred into the same role. From there, the sky's story jumps to the Greeks. You find yourself now under a marble colonnade in Athens around 300 BCE. Torches flicker against stone, and philosophers in robes gesture dramatically at the heavens. Aristotle claims the earth is the centre of it all. Obvious, he says, because heavy things fall toward the middle. And where else would the middle be but right here? Meanwhile, Aristarchus of Samos quietly suggests the sun might be the true centre. His idea is radical, borderline scandalous. It doesn't catch on, but centuries later we'll look back and nod, whispering, he was onto something. The Greeks loved geometry almost as much as they loved olives. They built cosmic models with circles upon circles, little orbits stacked like gears. Ptolemy's grand system, 1,000 years later in Roman Alexandria, took those circles and polished them into a full-blown manual, the Almagest. For more than a millennium, his earth-centered vision ruled. Sailors, monks, scholars, everyone navigated by a cosmos that revolved around us. It was comforting, if a little egotistical, like starring in a play where the whole set moves to keep you in the spotlight. Now, here's a quirky tidbit. The Greeks may have misjudged the universe's structure, but they nailed one detail shockingly well. Eratosthenes, around 240 BCE, used shadows cast at different cities to measure Earth's circumference. He got within a few percent of the real number, all with sticks, shadows and geometry. It's almost insulting how clever that is compared to our reliance on Google Maps. Historians still argue whether his method spread widely in his time, or if most people clung stubbornly to the flat Earth picture long afterward. Either way, his experiment is proof that curiosity doesn't always need high-tech tools, just imagination and patience. Step out of Athens now, drift further east, and you land in ancient China. Imperial astronomers there built massive star catalogues, mapping thousands of objects visible to the naked eye. They recorded novae, new stars suddenly blazing into view, centuries before Europeans even had the word. One famous record from 1054 describes a star so bright it was visible in daylight for weeks. We now know it was a supernova that created the Crab Nebula. Imagine being a court scholar, ink brush in hand, ordered to explain why the heavens themselves seemed to burst apart. Talk about job stress. The Mayans, across the ocean, were just as dedicated. Their temples align with solstices, equinoxes, even Venus's rising. Imagine crouching inside a stone observatory in Chichen Itza, sunlight slicing through the doorway exactly at the equinox. To them, the sky wasn't abstract, it was part of the architecture. Their calendar, more accurate than Europe's at the time, wove astronomy into daily life. It wasn't just timekeeping, it was rhythm, it was ritual, destiny. Back on your patch of grass, you start to realize that the urge to measure the sky is as old as civilization itself. Whether carving star charts into stone, aligning pyramids with Orion's belt, or timing planting seasons with Sirius's first appearance, humans always looked up to make sense of down here. And that makes you smile, because despite all our technology today, radio telescopes, space probes, orbiting observatories, the impulse is exactly the same. You want to know where you are. You want to know how big home really is. The funny thing, most of those early astronomers had no idea what stars actually were. Some thought they were tiny holes in a dome of night, letting divine light shine through. Others pictured them as fiery beads strung on invisible wires. And yet, without knowing their true nature, they still track them with obsessive care. It's like writing down your favourite song lyrics phonetically without knowing the language. You still catch the rhythm even if the meaning slips by. One last odd gem. The Babylonians also tracked Jupiter's motion with surprising sophistication. A clay tablet discovered in recent years showed they used a form of calculus, more than 1,000 years before Newton would invent it. You can almost hear modern mathematicians sighing, well, so much for originality. So tonight, as you lie back with stars scattered above, you're not alone in your gaze. You're in a lineage stretching back thousands of years. Farmers, priests, philosophers, mathematicians, all squinting at those same constellations, tracing shapes, measuring angles, daring to put numbers on infinity. And though their models have long been revised or overturned, the spirit remains. You're part of that same restless curiosity, staring into the dark not because you expect an answer, but because the asking itself feels human. You roll a little to your side in the grass, blinking slowly as your mind drifts from ancient astronomers toward the first cracks in their cosmic models. The Greeks and Babylonians had mapped the sky with obsessive detail, but the picture was still Earth-centered, comfortably human, like a universe built for us. But then you feel the timeline shifting, centuries sliding past, and suddenly you're in Renaissance Europe, surrounded by parchment, ink, and the stubborn smell of burning candles. It's here that the heavens stop revolving around Earth, and everything you thought you knew starts to tilt. Enter Copernicus. It's the early 1500s, and he's a quiet man in Poland, hunched over manuscripts, drawing circles and more circles. For decades, he works in secrecy, calculating a whole model where Earth isn't the main character. Instead, the sun claims the centre stage. He publishes his great work, De Revolutionibus Orbium Coelestium, in 1543, right before his death, possibly because he knew how controversial it would be. You can imagine him whispering, "Here you go, world, have fun arguing, Marie," and then conveniently exiting the stage. Historians still argue whether Copernicus truly feared backlash, or if he just wasn't much of a self-promoter. Either way, his sun-centered model cracked the cosmic ego bubble humanity had been living in for millennia. Now picture yourself in the streets of Italy some 70 years later. A man with wild hair and an even wilder temper is tinkering with polished glass tubes. Galileo Galilei has just pointed his homemade telescope at the heavens, and what he sees rattles the last bolts of the Ptolemaic model. 4 little moons orbiting Jupiter. Saturn looking strangely like it has ears. Those rings confused him. And most damning of all, Venus showing 4 phases just like the moon, something that only makes sense if Venus orbits the sun. Galileo, never one to keep quiet, publishes his findings with theatrical flair. He writes in Italian, not Latin, which means ordinary people can actually read it. Imagine a world where suddenly the cosmos is breaking news at the dinner table. "Honey, did you hear? Earth's not the centre anymore. Pass the bread." Naturally, the church isn't thrilled. In 1616, Copernicus's book lands on the banned list, and by 1630, Galileo's on trial. He's forced to recant, muttering his famous "and yet it moves" under his breath. A cheeky reminder that truth doesn't always wait for permission. Here's a quirky tidbit to tuck under your pillow. Galileo didn't invent the telescope. That honour belongs to Dutch spectacle makers in the early 1600s, but Galileo was the one who turned it toward the sky and said, maybe we should use this spyglass for spying on the universe. His decision shifted the telescope from novelty gadget to scientific weapon. Today, it's hard to imagine astronomy without it. From Galileo's spark, the revolution spreads. Kepler comes next, ditching the sacred perfect circles of Greek thought and showing that planets move in ellipses. No more tidy symmetrical loops, just slightly squashed orbits, with the sun sitting off-centre. It's less elegant, but it works. Newton eventually ties it all together with gravity, turning the heavens into a giant predictable clock. For the first time, you can describe both an apple falling and the moon orbiting with the same equation. The cosmos is still mysterious, but it's no longer inscrutable. And yet, this is where things get funnier than you'd expect. While Newton's laws explained planetary motion brilliantly, they still kept the universe finite in people's minds. Sure, Earth wasn't the centre, but many scientists still imagined the stars as a fixed backdrop, tiny lanterns glued to a celestial sphere just a little farther away than before. Historians still argue whether Newton himself believed in an infinite universe, or whether he imagined something more contained, with God occasionally winding the cosmic clock to keep it running smoothly. Meanwhile, across Europe, telescopes grow larger and sharper. Astronomers like William Herschel map the Milky Way, sketching its hazy disk by counting thousands of stars night after night. It's patient, tedious work, but it stretches the known cosmos even further. Herschel even stumbles across Uranus in 1971, the first planet discovered since antiquity. He wanted to name it after King George, which would have made the night sky painfully political. Imagine if you had to say, "Look, there's King George rising in the east tonight." Thankfully, the name Uranus stuck, though it still sparks giggles in classrooms centuries later. Here's where you pause in the grass, letting all of this swirl together. One by one, the heavens have expanded. From Babylonians charting Venus, to Greeks drawing circles, to Copernicus shifting the stage, to Galileo peeking through glass and shaking the world. Each step didn't just widen the universe, it shrank humanity's role inside it. Once upon a time, you were the cosmic centerpiece. Now, you're clinging to a small rock spinning around a middling star in a spiral arm of one galaxy among billions. Congratulations, you're officially downgraded. But strangely enough, that downgrade is liberating. The universe becomes more wondrous the less it belongs to you. Galileo's trial may have silenced him in his time, but the whisper of "and yet it moves" has never stopped echoing. You feel it even now as the wind brushes your cheek. The Earth is moving, the planets are circling, the stars themselves are drifting on epic scales. You're inside the motion, not outside of it. So tonight, as you lie here, you're not just looking up at pretty lights. You're staring through centuries of stubbornness, courage, and curiosity. You're inheriting a view of the universe that cost people their reputations, their freedom, sometimes their safety. And every star above you feels a little brighter for it, each one a reminder that truth doesn't orbit around comfort. It orbits around evidence, waiting patiently for someone curious enough to look. Your gaze softens as the stars blur slightly, and your mind drifts toward the problem Galileo and Copernicus never solved, the question of distance. Knowing that Earth moves around the sun is one thing, but how far away are those glittering dots above you? For centuries, no one could answer. The stars seemed impossibly distant, like lanterns hung on an unreachable ceiling. But then you recall the trick you practiced earlier with your finger, the way it jumps when you close one eye, then the other. That wobble, that little shift against the background, is called parallax. Astronomers realized they could use Earth's orbit like a pair of giant eyes separated by a dainty 6 million miles. 6 months apart, 2 vantage points, one tiny shift in a star's position, and suddenly the heavens have depth. The first to measure it successfully was Friedrich Bessel in 1838, who targeted a modest little star called 61 Cygni. It wasn't spectacular, as not even particularly bright, but it was close enough for its position to wiggle against the backdrop. From that wiggle, Bessel calculated the star was about 11 light-years away. 11 years for light to travel, a number so huge it rattled scientists of his day. For the first time, a star wasn't just a speck, it had a measurable address in the cosmic neighbourhood. Historians still argue whether Bessel deserved more fame than he got. After all, he cracked open the third dimension of the sky, but he never became a household name. Now picture this. The parallax shift astronomers chase is so small, it's less than 1 arcsecond. To give you scale, hold up a human hair at arm's length. That's about 30 arcseconds wide. They were detecting shifts 30 times smaller than that. It's like measuring the wiggle of a flea on the back of a running elephant viewed from miles away. No wonder it took until the 19th century to pull off. But once the door opened, it stayed open. With parallax, astronomers could start building a cosmic distance ladder. Nearby stars measured by parallax became the first rung. Then, by comparing the brightness of certain stars against those known distances, they created new yardsticks. Each rung extended farther than the last, like tossing rope bridges into the dark. Without parallax, the ladder never would have had a foundation. Here's a quirky tidbit. Bessel wasn't the only one racing to win this parallax contest. 2 other astronomers, Thomas Henderson in South Africa and Friedrich Struve in Russia, were hot on his heels. All 3 announced results within a single year. It was like a 19th century space race, only instead of rockets and circuits, they had telescopes and shaky handwriting in logbooks. If you imagine 3 rival scientists sitting at candlelit desks muttering at the sky, you wouldn't be far off. And what does parallax tell you lying here on the grass tonight? It whispers that the sky isn't flat. It's not a painted ceiling or a 2-dimensional dome. It's a vast 3D ocean, and you're just beginning to trace its contours. Each star is at a different depth, some near, some absurdly far, all drifting slowly through space. You could almost feel seasick thinking about it, like floating in a boat where the waves are made of light years. Of course, parallax has its limits. Beyond a few hundred light years, the shifts get too tiny for even the best Earth-based telescopes to detect. The stars blur together, their distances guessed by indirect means, but patience pays off. In 1989, the European Space Agency launched Hipparcos, the first satellite designed for astrometric precision. Suddenly, we weren't limited by Earth's shaky atmosphere. Hipparcos measured the distances to more than 100,000 stars, pushing the cosmic yardstick farther. Then came Gaia in 2013, a spacecraft so precise it can detect shifts as small as a few dozen micro-arc-seconds. That's like spotting a quarter on the moon from Earth. Gaia's catalogue now includes nearly 2 billion stars, giving humanity the most detailed 3D map of our galaxy ever assembled. Historians still argue whether we should call Gaia's work the greatest cartographic achievement in history. After all, explorers once filled in the edges of Earth's maps with sea monsters. Now we are charting stars tens of thousands of light years away, and the monsters are statistical uncertainties. But don't let the scale scare you. Think instead of how playful this method is. Astronomers literally wait for Earth to wobble around the sun, then watch how the stars wiggle. The whole planet becomes a measuring stick, a giant yard tool casually swinging through space. It's humbling but also charming, like using your entire house to squint at a speck of dust in the distance. And here's the cosmic punchline. Even though parallax gave us the first hard numbers, it only scratches the surface of the universe's true size. Measuring the nearby stars is like figuring out your neighbourhood by counting houses on your street. Useful, sure, but what about the next town, the next country, the faraway continents? For that, astronomers needed brighter, more distant yardsticks, something you'll wander towards soon. For now, you let the word parallax drift lazily in your mind, the sound almost soothing, like a lullaby for the cosmos. Each star above you is a point of data gently shifting as Earth swings through space. The ancient stargazers never had this trick, but they would have loved it. Another way of making the heavens a little less mysterious, a little more human. And as you breathe deeper, you feel the wobble of Earth itself, spinning, orbiting, rocking you like a cradle suspended in starlight. Your breath is steady, and the night sky feels almost too quiet until you remember it's anything but still. Those stars above aren't pinned like wallpaper, they're racing, the whole universe expanding around you. And here your mind drifts toward Edwin Hubble, the man who finally proved it. Imagine yourself in 1924, standing on a cold mountaintop in California. The wind bites your ears, your hands are stiff from scribbling notes, and behind you looms the 100-inch Hooker telescope, the largest in the world at the time. Hubble peers through that glass and sees something no one expected. Fuzzy smudges, once thought to be nearby gas clouds, are actually galaxies, entire islands of stars millions of light years away. The universe just got a lot bigger, and everyone's mental wallpaper ripped at the seams, but Hubble didn't stop there. He noticed something odd about those galaxies. Their light was stretched, shifted toward the red end of the spectrum. It's the same effect you hear when an ambulance zooms by. The pitch of the siren drops as it speeds away. Galaxies, it turned out, were doing the same trick. The farther away a galaxy was, the redder its light appeared, meaning it was rushing away faster. Hubble plotted the numbers and found a pattern. Distance and velocity went hand in hand. The farther away the galaxy, the faster it was fleeing. The conclusion? The universe is expanding. Not the galaxies flying through empty space, but space itself stretching like a rubber sheet. Historians still argue whether Hubble fully grasped the implications when he published his results in 1929, or whether he was simply reporting data without realizing he had rewritten the cosmic rulebook. Either way, his discovery shattered the old idea of a static, eternal universe. Instead, you had a cosmos that was dynamic, alive and growing. Here's a quirky tidbit. Hubble was such a celebrity scientist in his time that he once received a ticker-tape parade in New York City, the kind usually reserved for war heroes. Imagine confetti raining down because you proved galaxies are running away. That's the kind of science clout you don't see every day. Lying in the grass now, you picture the galaxies fleeing like dancers in slow motion, carried on a floor that keeps stretching beneath their feet. The night sky doesn't look like it's moving to your eyes, but the redshift data doesn't lie. Every point of light is part of a vast choreography, drifting farther apart with each passing second. Some galaxies are already receding so quickly that their light will never reach us again. It's bittersweet. You can see them now, but future observers won't. The universe is erasing its own history as it goes. Redshift, of course, became the next rung of that cosmic distance ladder. If you measure how stretched the light is, you can estimate how far away a galaxy sits. Combine that with parallax and other methods, and suddenly you have a way to measure not just the stars in your neighbourhood, but the very scale of the cosmos itself. The numbers balloon quickly. Instead of a Milky Way surrounded by a few nearby clusters, astronomers found billions of galaxies spread across space in every direction. If you ever feel like your problems are too big, just remember, entire galaxies are sprinting away from each other at millions of miles per hour, and they're not complaining. But the expansion comes with puzzles. For one, why is it happening at all? The early explanation was simple inertia. The universe exploded in the Big Bang, and everything's been coasting outward ever since. But later data, especially from the 1920s onward, showed the expansion isn't slowing down, it's speeding up. Some mysterious force, now called dark energy, seems to be pushing everything apart even faster. That discovery will come later in your journey. But for now, you're content to picture the universe as an endless loaf of raisin bread baking in the oven. Each raisin is a galaxy, and as the dough rises, all the raisins move apart. Not because they're running, but because the dough itself is stretching. And in this kitchen of cosmic scale, the oven never turns off. One of the stranger debates among scholars today is whether Hubble's original law, the neat straight line of distance versus velocity, is perfectly smooth or a little messy. The Hubble constant turns out to be not so constant after all, with different measurement methods giving slightly different answers. Historians still argue whether this tension hints at some new physics or just stubborn data quirks waiting to be ironed out. Either way, it's a reminder that even the most famous discoveries are works in progress, not finished scripts. Back on Earth, though, in your patch of grass, the expansion is invisible. The stars overhead look steady, their constellations unchanged since ancient times. But if you could fast forward the sky, compress millions of years into seconds, you'd see Orion stretch and warp as its stars drift apart. You'd see galaxies vanish over the horizon of visibility, their light swallowed by the expansion. It would be beautiful and heartbreaking, like watching fireworks fade in reverse. And here's the light-hearted joke your sleepy brain can't resist. If everything in the universe is expanding, technically even your pillow's getting bigger. But don't worry, the effect on household furniture is so tiny it's basically cancelled out by the strength of your bed springs. Cosmology is grand, but not grand enough to spare you a lumpy mattress. So tonight, you lie here under an expanding sky, thinking of Edwin Hubble squinting into his telescope, not knowing he was handing humanity its biggest reality check. The universe isn't static, it isn't centered on us, and it isn't small. It's alive with motion, a restless tide of galaxies, red-shifting endlessly into the dark. And somehow knowing that makes the night feel even calmer, as though you've caught the rhythm of something vast, steady, and eternal in its very change. You close your eyes for a moment, and the universe hums around you, not with sound, but with a kind of background presence. Imagine it, the afterglow of creation itself, faint but everywhere, woven into the fabric of space like a cosmic lullaby. That hum is real. Scientists call it the cosmic microwave background, or CMB for short. And it's one of the strangest, most comforting discoveries in all of astronomy. To picture it, think of the universe as a newborn. Right after the Big Bang, it was a hot, glowing plasma, so bright and dense that light couldn't travel freely. It was like living inside a star, where photons keep bouncing off particles instead of escaping. Then, about 380,000 years later, the cosmos cooled just enough for atoms to form, and suddenly light could break free. That first release is still streaming across the universe today, stretched into faint microwaves by billions of years of expansion. The CMB was first detected by accident in 1965 by Arno Penzias and Robert Wilson. They were radio engineers, not cosmologists, fiddling with a big horn-shaped antenna in New Jersey. The thing kept picking up a weird static no matter where they pointed it. They even cleaned out pigeon droppings from the equipment, thinking that might be the culprit. But the hiss wouldn't go away. Turns out it wasn't pigeons. It was the afterglow of the Big Bang itself. Historians still argue whether they fully appreciated the significance right away, or if the nearby Princeton team that had been hunting for it deserved more of the credit. Either way, two confused engineers walked into a Nobel Prize, proving the universe had a fiery beginning. Here's a quirky tidbit. If you own an old analog TV and turn it to a static-filled channel, about 1% of that fuzz comes from the CMB. That means every time your grandparents smack the side of the TV trying to fix the picture, they were literally touching the echo of the universe's birth. Kind of poetic, if a little noisy. For scientists, the CMB was more than just proof of the Big Bang, it was a treasure map. When satellites like COBE in 1989 and later WMAP and Planck scanned the sky, they found the microwave glow wasn't perfectly smooth. Tiny fluctuations, mere differences of 1 part in 100,000, spotted the sky. Those faint ripples are the seeds of galaxies. Imagine you're staring at a grainy baby photo of the universe where every little blotch marks the future of stars, clusters, and the cosmic web itself. It's humbling to think that your galaxy, the Milky Way, was once just a cold blue dot in that early pattern. Historians still argue about the finer details of the CMB, whether those fluctuations point to certain shapes of inflation, or if they hint at anomalies we don't fully understand. There's even debate over whether a cold spot in the southern hemisphere of the map is just random chance or evidence of something weirder, like a collision with another universe. The safe answer is, no one knows. The thrilling answer is, maybe. Lying back in the grass, you imagine the sky not as stars but as a faint invisible glow in every direction. It's not something your eyes can see, but if you could shift your vision to microwaves, the heavens would blaze with that soft, uniform light. The entire universe has a temperature, about 2.7 Kelvin, just a whisper above absolute zero, set by this ultraviolet radiation. Think about that. The cosmos still carries the chill of its earliest moments, and every atom in your body is bathed in that afterglow right now. The CMB also gave scientists a way to measure the universe's size more precisely. By analysing the scale of those fluctuations, they could estimate how much matter, dark matter, and dark energy make up the cosmos. They could even tell how fast it's expanding. Without the microwave background, the numbers would be wild guesses. With it, we have something close to a cosmic blueprint. It's as if the baby photo came with a caption explaining how tall the child would grow and what career they might pursue, and yet there's something strangely intimate about it. This light has been travelling for 13.8 billion years just to reach you tonight as you lie in the grass. Longer than Earth has had oceans, longer than the sun has been shining, each photon has crossed the cosmos like a patient messenger, carrying a story of the first time the universe took a breath. And now, here you are, letting that story wash over you. Of course, your brain might whisper, does that mean the universe has an edge? A place where this light was born? Not exactly. The CMB isn't the edge, it's the fog clearing after the first flash. Beyond it, the universe is older than light itself. The photons are just the earliest visible record, like the first legible page in a book that was already being written. Historians still argue how much we'll ever be able to see past that rock, or if the CMB is the final curtain on observable history. Here's a joke to soften the weight. You could say the universe is basically a giant baby picture, and we've been analysing its pixel resolution for decades. The only difference is, instead of doting grandparents pinning it to the fridge, we launch billion-dollar satellites to frame it in microwave light. So tonight, as you breathe slower and your body sinks deeper into the grass, the thought lingers. The universe has left fingerprints everywhere, faint but undeniable, etched into the background of space itself. That static hiss, that baby blue glow, is proof you belong to a cosmos with a history, a childhood, a memory of its own beginning. And somehow that makes the dark around you feel warmer, like you're wrapped not just in a blanket of stars, but in the very first light the universe ever released. The night air is cool on your skin, but your thoughts are glowing like embers, warming as you climb the next rung of the cosmic ladder. Standard candles. The phrase sounds almost cozy, like something you'd buy at a home goods store, but in astronomy it means something far stranger. Objects so predictable in brightness that they can be used as cosmic yardsticks, and the star that really steals the show? The supernova. Picture yourself standing beneath the ancient sky of 1054. Suddenly, a new star appears, so bright it outshines Venus, so bright it can be seen in the daylight. For weeks, it burns like a heavenly lantern, and then slowly fades, leaving behind what we now call the Crab Nebula. Chinese and Japanese astronomers recorded it carefully, but in Europe the event barely appears in surviving records. Historians still argue whether medieval Europeans simply missed it, whether their cloudy weather blocked the view, or whether church authorities hushed it up as theologically awkward. After all, a new star didn't fit neatly with the idea of a perfect, unchanging heaven. Supernovae have violent ends for massive stars, but their usefulness comes in how consistent they can be. Certain types, called type-ear supernovae, always detonate with nearly the same brightness. Why? Because they all start from the same recipe. A white dwarf star stealing gas from a companion until it tips over a critical mass, at which point it ignites in runaway fusion. The explosion is catastrophic, But the payoff for astronomers is that these blasts are like cosmic 100-watt bulbs. Wherever they go off in the universe, you know how bright they're supposed to be. Measure how bright they look to us and you can calculate their distance. It's like recognizing the wattage of a street lamp and judging how far down the road it stands by its glow. Here's a quirky tidbit. In 1572, a young Danish astronomer named Tycho Brahe spotted a new star in the constellation Cassiopeia. He documented it with such precision that his name is still attached to the remnant, Tycho's supernova. The kicker? He wrote a book about it while wearing a metal nose. Yes, Tycho lost part of his real nose in a duel and replaced it with a prosthetic, probably made of brass. Imagine trying to measure the heavens with half your face patched up and still doing it better than anyone else in Europe. Standard candles don't stop at supernova. Variable stars, particularly Cepheids, also shine into predictable rhythms. Henrietta Swan-Leavitt, an underappreciated astronomer working at Harvard in the early 1900s, discovered that the brighter a Cepheid star, the longer its pulsation period. That meant you could simply time its twinkle and know its true brightness. Hubble himself used Cepheids to measure the distance to Andromeda, proving it was a separate galaxy, not just a cloud in our Milky Way. Without Leavitt's discovery, Hubble's great revelation might have taken decades longer. Historians still argue whether she should have shared a Nobel Prize posthumously, since her work laid the foundation for modern cosmology. Tonight, as you lie in the grass, you imagine the universe flashing with these cosmic beacons, Cepheids pulsing steadily, like lighthouses turning over galactic seas, supernovae flaring briefly like fireworks exploding in slow motion. Each one is both a tragedy, the death of a star, and a gift, handing you a yardstick stretched across millions or even billions of light years. The irony is almost comic. Stars have to die dramatically so that humans can measure how far away their neighbours are. You could say the universe is generous, but with a dark sense of humour. The discovery of standard candles also reshaped how we talk about the size of the universe. With Cepheids, we could measure nearby galaxies. With Type Ia supernovae, we could leap much farther, mapping out entire clusters. And in the 1990s, Temne using these supernovae stumbled on something shocking. Galaxies weren't just moving apart, they were accelerating. That's how dark energy muscled its way into the conversation, turning from a fringe speculation into one of the central mysteries of cosmology. But that's a story waiting a few sections down the road. For now, you picture each standard candle as a milestone in a dark highway. Every time one flashes, you get another data point, another chance to measure just how far the road stretches. The observable universe isn't just a vague blur anymore. It's a place with numbers attached, precise enough to draw maps. Scientists now use these tools to calculate the Hubble constant, to test whether the expansion rate lines up with the predictions of the cosmic microwave background, and to argue endlessly at conferences about why their results don't quite match. It's a reminder that measuring the universe is less about certainty and more about comparing notes at a cosmic group project. Here's a little joke for you to hold on to. Astronomers call them standard candles, but anyone who's ever bought candles at a store knows none of them ever burn the same way. Vanilla-scented ones melt in a tunnel, tea lights gutter out early, and those 3-wick monsters turn your living room into a bonfire. Luckily, stars have better quality control, and so you lie back feeling the pulse of Cepheids and the flash of supernovae, flickering somewhere billions of light years away. The night sky looks calm, but underneath it is a universe where stars live, breathe, collapse, and detonate in ways that let you measure distances too vast to comprehend. Each flicker is a ruler, each explosion a mile marker, all of them whispering the same truth. The universe is not just infinite in wonder, it's measurable, at least in parts, by the light of stars that burn themselves out to illuminate the road ahead. Your body is heavy in the grass now, but your thoughts keep floating backward, farther than parallax, farther than Cepheids, farther even than the first supernovae. They slip into the earliest instant of everything, the first second of the universe's life. Imagine the cosmos not as stars and galaxies, but as a newborn spark, smaller than a proton yet holding everything that would ever exist. In that incomprehensibly tiny instant, something extraordinary happened. Inflation. Not the kind that makes grocery prices unbearable, but a burst of expansion so violent and so fast that the universe grew from subatomic size to astronomical size in less time than it takes you to blink. Inflation theory was proposed in the early 80s by Alan Guth, who tried to solve several riddles left behind by the standard Big Bang model. For instance, why does the universe look so uniform in every direction, even though distant regions should never have been in contact? Why is space so flat when gravity should have bent it like a warped record? Inflation was the elegant cheat code. By stretching space faster than the speed of light, don't worry, relativity allows the fabric of space itself to expand that way. It ironed out wrinkles, spread energy evenly, and set the stage for galaxies. Historians still argue whether inflation is proven fact or just a clever patchwork. The equations line up, but the evidence is indirect. One of the best tests would be to find subtle patterns in the cosmic microwave background, tiny swirls left over from primordial gravitational waves. In 2014, astronomers at the BICEP 2 experiment in Antarctica thought they'd found exactly that, sparking headlines about smoking gun evidence for inflation. But the signal turned out to be dust and ordinary interstellar particles glowing in the microwave sky. Inflation had to retreat back into theory, still waiting for confirmation. Here's a quirky tidbit. The expansion during inflation was so extreme that regions once smaller than atoms were flung beyond our observable universe in a fraction of a second. If you ever complain about jet lag after a long flight, just remember the universe once travelled farther in an instant than you'll ever manage in a lifetime. Talk about overachieving. Lying in the grass, you picture inflation like blowing up a balloon. 1 second it's small, wrinkled, and uneven. Then, with a single puff, it smooths out into a perfect sphere. On that balloon, tiny quantum jitters, fluctuations too small to imagine, get stretched into the seeds of galaxies. Every cluster of stars, every nebula, every black hole, even you yourself, ultimately trace back to those microscopic jitters amplified by inflation. The universe is a giant quilt stitched from quantum threads. The philosophical weight is staggering. If inflation really happened, it also implies the universe is vastly larger than the part we can see, maybe infinite. Because while our observable bubble is 93 billion light-years across, inflation would have stretched the fabric far beyond that into regions we'll never observe. Some versions of inflation even suggest it never really ended. Instead, different pockets of space kept inflating, birthing bubble universes beyond our reach. Historians still argue whether this so-called eternal inflation deserves serious attention or belongs in the speculative playground alongside multiverse fan fiction. And yet, the idea has a strange, sleepy comfort to it. You lying here in the grass, tracing constellations with your finger, could be one bubble among countless others, each with its own physics, its own galaxies, maybe its own version of you also staring at the stars. It's humbling, but it's also oddly soothing. Like realizing your worries don't have to be the center of reality. The inflation model also gave cosmologists tools for measuring the universe's actual size. By comparing predictions of flatness, uniformity, and fluctuation patterns to observations of the microwave background, they concluded the universe has to be at least hundreds of times larger than the observable part. In other words, our 93 billion light-year bubble is just a pinprick. Even if the universe were finite, it would still be unimaginably bigger than anything we can see. It's like realizing your backyard is just one blade of grass in a prairie stretching beyond the horizon. Of course, not everyone is sold. Some physicists argue inflation introduces more questions than it answers. What caused it? What ended it? And why should quantum jitters scale up so neatly? Historians still argue whether Guth's original model was too simplistic, whether modifications will eventually save it, or whether some entirely new theory will sweep in and replace it. Science, like the cosmos itself, expands with time. But for you tonight, drifting under the stars, the story of inflation is like a bedtime myth of the highest order. Once upon a time, the universe was small and hot and crowded. Then, in a breathless instant, it grew so vast that light itself is still catching up. From that moment came galaxies, planets, life, and eventually you, lying here, listening to the faint whisper of your cosmic origins, and here's the joke your drowsy mind clings to. The universe inflated faster than the speed of light, but your laundry still refuses to dry any quicker. Apparently cosmic inflation doesn't take requests, so you let the thoughts settle. The grass cradles you, the night air brushes your cheek, and overhead the sky stretches wider than your imagination. Every star, every flicker of light is a reminder that once upon a time, the entire cosmos was small enough to fit inside a teacup before it exploded into infinity. The grass rustles faintly under your shoulders, but you hardly notice, because now your mind drifts outward, far beyond parallax and Cephites, beyond inflation's wild beginnings. You begin to picture the universe not as a random scattering of galaxies, but as a structure, an intricate ghostly web stretched across billions of light years. This is the cosmic web, the large-scale architecture of the universe, and if you could float far enough back to see it in full, the view would knock the breath from your chest. Galaxies aren't just sprinkled like salt, they gather in vast filaments, looping together in strands that weave across unimaginable distances, with yawning voids of near-nothingness between them. The first hints of this pattern came in the 1980s, when astronomers began compiling redshift surveys of thousands of galaxies. Plot them out in 3 dimensions, and suddenly the universe looked less like a fog and more like a sponge. Dense threads and clusters separated by hollow gaps. Today, with modern surveys like Sloan Digital Sky Survey, we've mapped millions of galaxies, and the pattern is clear. The cosmos is a cosmic web, filaments stretching across the darkness like dewdrops on invisible silk. Historians still argue whether the web analogy was the first image that leapt to scientists' minds, or whether someone later realised sponge wasn't quite poetic enough for the press release. Here's a quirky tidbit. The largest structure we've named in the universe is the Hercules Corona Borealis Great Wall, a titanic filament of galaxies nearly 10 billion light-years across. It's so large that some scientists question whether it violates the assumption that, on the biggest scales, the universe should look roughly uniform. If the cosmic rulebook says no one region should dominate, then this Great Wall is basically graffiti across the page. Some researchers cheerfully accept it, others insist it's a statistical fluke, and yes, historians still argue whether it even counts as a single structure or just a happy accident of clustering. Lying in the grass, you imagine zooming outward, far beyond the Milky Way, far beyond the local group, far beyond the Virgo cluster. As you pull back, galaxies fade into threads, and threads link into filaments, and the whole view begins to look eerily familiar. Like neurons in a brain, like veins in a leaf. Like cracks in frozen glass. It's tempting, maybe too tempting, to think the universe is a kind of giant mind, its galaxies firing like synapses. That's poetic more than scientific, but the resemblance lingers like a trick of the eye. One of the most stunning projects to capture this is the Millennium Simulation, a computer model that tracks billions of particles of dark matter and gas evolving over cosmic time. Run the math and filaments emerge naturally, forming the scaffolding on which galaxies gather. It's like shaking a snow globe and watching the flakes settle into delicate lace. The fact that a computer model can reproduce the same web we see in telescopes is one of the triumphs of modern cosmology. But what does the cosmic web really mean for you, lying here in your quiet patch of grass? It means that your galaxy, your sun, even you, are part of a filament billions of light years long. You're not floating in empty space. You're wired into a colossal structure, a strand among countless strands. And the voids between those strands, immense bubbles where almost no galaxies exist, are just as important. They define the texture, the hollows that make the web stand out. The biggest of these voids can be hundreds of millions of light years across. To put it in human scale, imagine driving for 100 lifetimes at highway speed and still not finding a single star. That's what a cosmic void feels like. And yet, those voids are beautiful in their own right. They show how gravity has sculpted the cosmos. Where matter is dense, galaxies form clusters and filaments. Where it's sparse, space remains empty. Over billions of years, the universe has sorted itself like cream rising in coffee, leaving swirls and gaps that, together, paint the grandest pattern ever seen. Here's your joke for the night. If galaxies are beads on filaments, then the universe is basically the world's largest string of holiday lights, though admittedly less festive and much harder to untangle. Mapping the cosmic web also lets scientists test theories about dark matter and dark energy. The filaments match where dark matter is predicted to lie, forming invisible highways along which galaxies migrate. And the rate at which the web grows, or the way it stretches with time, reveals clues about the mysterious acceleration of the universe. The web isn't just pretty, it's diagnostic. Like veins under the skin hinting at the blood flow beneath. Historians still argue about the philosophical weight of this discovery. In the 9th century, humanity thought of the cosmos as a scattered starfield, immense but simple. Now we know it has a skeleton, a hidden design, a geometry that ties it all together. Some call it a new Copernican moment, another humbling step away from imagining ourselves at the centre. Others shrug and say, well, of course matter clumps, what did you expect? But to you, lying here, it feels miraculous that such order emerges from chaos. So tonight, you picture yourself suspended on one strand of that infinite web. Your galaxy glimmers like a bead of dew, connected to others by filaments of unseen matter, stretched across distances your eyes can't even pretend to comprehend. And in that vision, you don't feel small. You feel connected, woven into the fabric of something far grander than yourself, a pattern written in galaxies and silence. The night feels deeper now, the air cooler, as though the silence itself is leaning closer to listen. You've wandered through the cosmic web in your thoughts, traced its delicate filaments, and now you're ready to tug at what holds that web together. Because if galaxies are the beads and filaments are the threads, then what's the hidden loom? The answer is something you can't see, can't touch, and can't taste, but which outweighs everything visible: dark matter. Imagine lying in the grass and staring at the Milky Way arcing overhead. You see its river of starlight, billions of suns swirling together, glowing like spilled milk. But here's the twist. All that light, all that matter, planets, stars, gas, even you, adds up to less than 20% of what the galaxy really contains. The rest is invisible mass, a hidden scaffolding of dark matter shaping everything from galaxy rotations to the grand web itself. Without it, the stars would fly apart like sparks from a firework. The first serious hints came in the 1930s from a Swiss astronomer named Fritz Zwicky. He was studying the Coma cluster, a swarm of galaxies bound together, and noticed something odd. They were moving too fast. By his calculations, visible matter alone wasn't nearly enough to hold them in place. Something unseen, something he cheekily called dunkel materia, dark matter, had to be providing the extra gravity. Historians still argue whether Zwicky was brushed off because his data seemed outlandish, or because he was notoriously abrasive. Colleagues nicknamed him the terrible-tempered Swiss, which may not have helped his case. Here's a quirky tidbit. Zwicky once proposed turning the entire Mount Palomar telescope into a weapon by using its mirrors to focus sunlight and burn enemy ships at sea. It never happened, thankfully, but it tells you a lot about the man's flair for dramatic ideas. Fast forward to the 1970s, and another astronomer, Vera Rubin, provided the clinching evidence. She measured the rotation curves of galaxies, how fast stars orbit at different distances from the centre. According to Newtonian physics, the farther out you go, the slower stars should orbit, just like planets in the solar system. But Rubin found that stars in the outskirts of galaxies were moving just as fast as those near the centre. The only way to explain it was if each galaxy was embedded in a massive halo of unseen matter. Dark matter wasn't just a cluster problem, it was everywhere. Historians still argue whether Rubin should have received a Nobel Prize for her discovery. Many scientists believe she was overlooked, partly because her work was incremental rather than flashy, partly because she was a woman in a male-dominated field. Either way, her careful measurements reshaped cosmology forever. Tonight, lying in your patch of grass, you imagine those invisible halos. Vast clouds surrounding every galaxy like ghostly cocoons. They don't shine, don't glow, don't interact with light, but their gravity bends the paths of stars, warps the shapes of galaxies, even lenses distant light into arcs and rings we can see with telescopes. Dark matter is like the skeleton under the skin, never visible, always essential, and yet we don't know what it is. Particle physicists hunt for exotic candidates. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, but so far nothing has shown itself in detectors buried deep underground or blasted with beams and colliders. Some fringe theories suggest maybe it isn't a particle at all, but a flaw in our understanding of gravity itself. Modify the equations, tweak the rules, and maybe you don't need dark matter. Historians still argue whether dark matter is real stuff, or just an elegant placeholder for our ignorance. Here's the light-hearted joke your brain throws in. Dark matter is basically that one roommate who never pays rent, never leaves a trace, but somehow keeps the whole household from falling apart. For cosmologists, though, the existence of dark matter is less about philosophy and more about necessity. Without it, galaxies wouldn't hold together, clusters wouldn't form, the cosmic web wouldn't weave its filaments. Even the microwave background fluctuations make no sense without it. The universe as you know it, structured, luminous, patterned, requires dark matter as its invisible glue. And the strangest part? Dark matter outweighs regular matter by a factor of 5 to 1. Everything you can see, stars, planets, nebulae, is just a small side dish. The main course is hidden, silent, untouchable. When you brush your hand against the grass, you feel solid earth beneath you. But in cosmic truth, you're barely grazing the tip of an unseen iceberg. Lying here, that thought could be terrifying, but instead it feels calming. The invisible is holding you, literally. Without it, there'd be no Milky Way, no sun, no earth, no grass, no breath rising softly from your chest. Dark matter may be unknowable for now, but it's also your most reliable companion, an unseen anchor against the void. The night has grown so quiet that even the insects seem to have dozed off. But the universe around you is anything but still. You've traced the scaffolding of dark matter, the invisible backbone holding galaxies in place. Now your mind slides towards something stranger still, the force not pulling things together, but pushing them apart. Dark energy. The phrase sounds like it should belong in a comic book, some sinister power wielded by a villain in a cape. But in truth, it's less theatrical, more relentless, and infinitely harder to understand. For decades after Hubble showed the universe was expanding, scientists assumed gravity would eventually slow it down. Maybe the cosmos would coast gently forever. Maybe it would reverse and collapse in a big crunch. Either way, the expectation was simple. Expansion slows with time. But in the 90s, astronomers studying distant Type Ia supernovae, the trusty standard candles, stumbled onto something bizarre. Those galaxies weren't slowing. They were accelerating away, as though some hidden force was pushing the universe to expand faster and faster. Historians still argue whether the two independent teams who announced this result in 1998 truly expected it, or whether they were as shocked as the rest of the scientific world. Either way, their discovery won them the Nobel Prize in Physics in 2011, and it shoved dark energy into the spotlight. Suddenly the cosmos wasn't just coasting, it was running, pulled by something no one could see. Here's a quirky tidbit. Einstein himself had toyed with the idea of a cosmic repulsion nearly a century earlier. He called it the cosmological constant, a fudge factor he added to his equations of general relativity to keep the universe static. When Hubble showed expansion was real, Einstein reportedly called that constant his greatest blunder. And yet after the 1990s discovery, scientists resurrected the idea. Maybe Einstein's blunder wasn't so blunderous after all, so what is dark energy? The frustrating answer? No one knows. It might be a property of space itself, an energy woven into the fabric of the vacuum. It might be some new kind of field or force, or maybe it's an illusion caused by our incomplete understanding of gravity. Historians still argue whether we should even call it energy, since that word implies we understand far more than we actually do. Lying in the grass, you imagine space itself stretching, not because galaxies are running, but because the very stage they sit on keeps expanding beneath them. It's like drawing dots on a balloon and then blowing it up. The dots don't move across the surface itself grows. Dark energy is the air in that balloon, invisible but irresistible. And here's the kicker. Dark energy makes up about 70% of the universe. Ordinary matter, the stuff you can see and touch, barely registers on the cosmic pie chart. The cosmos is mostly dark matter and dark energy, with humans clinging to the leftovers. The discovery reshaped how we think about the ultimate fate of everything. If dark energy keeps doing its thing, galaxies will drift so far apart that trillions of years from now, even neighbouring clusters will vanish over the horizon. The night sky will empty out until only the faint glow of your local stars remains. If dark energy grows stronger with time, it could eventually rip galaxies, stars, even our atoms apart in a big rip. If it weakens, maybe the universe will coast more gently or even crunch back in. Each scenario is terrifying in its own right, but lying here tonight, they feel oddly abstract, like bedtime stories told on a scale too vast to worry about. Here's the light-hearted joke. If dark energy is pushing everything away from everything else, you could argue it's just the universe inventing the world's most elaborate excuse for social distancing. Scientists today study dark energy with massive surveys, scanning millions of galaxies to measure how structures evolve over time. The Euclid mission, launched by the European Space Agency in 2003, is designed to map billions of galaxies with exquisite precision, hoping to tease out the fingerprints of dark energy on cosmic scales. Projects like the Vera C. Rubin Observatory will soon add even more detail, turning the night sky into a rolling movie of expansion. And yet, despite the fancy tools, the mystery remains stubborn. Dark energy is like a magician you can never quite catch in the act. Historians still argue whether future generations will look back on our current theories with amusement, the way we now chuckle at Ptolemy's circles within circles. Maybe dark energy will turn out to be a placeholder, a word we invented to cover our ignorance until something better comes along. But tonight, lying here, the name feels fitting. It's dark because we can't see it. It's energy because it does work, and it's a reminder that the universe doesn't owe us easy answers. So you let your breath slow, your chest rising and falling in rhythm with the stars above, and you picture yourself afloat in a cosmos driven apart by a force you'll never feel directly. Galaxies slip like lanterns on a tide. Dark matter holds the skeleton together, and dark energy stretches the canvas wider every second. It's unsettling, yes, but it's also oddly peaceful. Because whatever dark energy is, it's not hostile, it's not malicious, it's simply the rhythm of the universe itself, an expansion that carries you gently along, cradled in grass and starlight. The night feels endless, your breath sinking with the whisper of the breeze, and your thoughts slide into the greatest balancing act of all, the difference between the observable universe and the entire universe. It's a bit like sitting in a room with a flashlight. The beam shows you a circle of floor and wall bright and clear, but beyond that glow is more space you simply can't reach. What scientists call the observable universe is our circle of light, the region from which the photons have had time to arrive since the Big Bang. Right now, that circle stretches about 46 billion light-years in every direction, giving a diameter of roughly 93 billion light-years. That's the bubble of cosmos you get to see. Beyond it, the dark, possibly infinite, possibly something stranger. This distinction is essential. People often imagine the universe is 93 billion light-years across, but that's only the observable patch. The real universe could be hundreds of times larger, or truly infinite. Historians still argue whether Einstein leaned toward a finite, closed cosmos, or whether he was content to leave the question open-ended. Some physicists say it's like trying to measure the size of an ocean while floating on a single boat. You see waves all around, but you can't be sure whether the water stretches forever or ends just beyond your horizon. Here's a quirky tidbit. In 2003, scientists used data from the cosmic microwave background to test whether the universe might be a finite shape like a dodecahedron, a 12-sided die. The idea was that light could wrap around and repeat, like living in a hall of mirrors, but no repeating patterns were found, at least not at the scales we can measure. The universe might still be finite in some bizarre geometry, but if it is, it's too large for us to notice. Lying in the grass tonight, you imagine standing at the very edge of the observable bubble. You look outward and see the microwave background, the faint afterglow of creation, stretched thin over the horizon of visibility. But you know beyond that horizon, galaxies keep forming, stars keep burning, planets keep circling, suns. The cosmos doesn't just stop where your view does. That's like assuming your flashlight's beam is all that exists in the forest. And this realization leaves you hovering in a strange limbo. You can measure a number, 93 billion light-years, yet admit with equal honesty that the true size might be unmeasurable. The concept of inflation only sharpens the point. If the early universe really did balloon at superluminal speed, then our observable bubble is a mere speck in a much larger whole. You can think of it like a soap bubble resting on an infinite froth. Your bubble is round, clear, measurable, but the froth goes on forever, bubbling with other universes you'll never see. Historians still argue whether it's useful to even talk about beyond the observable, since by definition we can't collect evidence there. But the temptation is irresistible. Humans don't like stopping at here's the edge of what you can see. You want to peek, to push, to ask, what's next? And yet, there's something wonderfully human about focusing on what's visible. Astronomers build telescopes that stretch vision to its limits, climbing as close to the horizon as physics allows. Satellites like Planck and James Webb turn the faintest flickers of photons into maps and spectra, pulling details from the edge of sight. It's as though humanity is standing on tiptoe, reaching as far as possible, even while knowing there's more they'll never touch. Here's a gentle joke for your sleepy mind. The observable universe is basically the cosmic version of your Wi-Fi signal. It's not that the internet stops beyond your house, it's just that your router's reach does. So tonight, you hold both truths in your thoughts. On one hand, the observable universe is immense, 93 billion light-years across, filled with 2 trillion galaxies, each one hosting billions of stars. It's enough to keep astronomers busy forever. On the other hand, it might be just a grain of sand on an endless beach, a candle flickering in a cathedral too vast to enter. That paradox doesn't feel frustrating. It feels calming. The universe has limits you can measure and mysteries you can't. Both truths coexist, like your breath and your heartbeat, finite, yet part of something larger. The grass beneath you cools, the sky above you stretches, and your eyes grow heavy. You let the thought of that great horizon drift in your mind, not as a wall, but as a gentle boundary, the edge of the light you can gather. Beyond it lies whatever lies beyond, waiting in silence, forever out of reach. And that's okay. You don't need to see it all to feel the immensity of it. The part you glimpse is already more than enough to fill a lifetime of awe. Your eyelids are heavy, but your thoughts drift outward, all the way to the farthest horizon of light. You imagine standing at the edge of the observable universe, right where the cosmic microwave background glows like the faintest ember. It isn't an edge in the usual sense, no wall, no boundary you can knock on, but a curtain of time. Beyond it, photons haven't had long enough to reach you, so the universe remains invisible. You picture yourself pressing your hand against that curtain, feeling the warmth of the first light seeping through, knowing that on the other side lies a path so dense and hot that it can never be seen directly. That horizon is about 46 billion light-years away in every direction, but it isn't static. Every second as you lie here, the horizon expands. More light from distant regions finally completes its journey, trickling into your telescopes, into your eyes. Yet at the same time, thanks to dark energy, many galaxies beyond that curtain are racing away faster than light, slipping permanently out of reach. The horizon is both a gift and a thief, offering you new sights, even as it snatches others away forever. Historians still argue whether it's more poetic to call it a cosmic light cone or an event horizon, but either way, it defines your view of reality. Here's a quirky tidbit. Astronomers once thought we might eventually see all of the universe if we just waited long enough, but the accelerating expansion proved otherwise. No matter how patient you are, even if you live trillions of years, you'll never see beyond a certain boundary. The cosmos is playing hide and seek, and it always wins. Lying in the grass, you imagine the view from that ultimate horizon. The sky wouldn't be filled with stars, but with a smooth fog of microwaves, faint but uniform, glowing at just 2.7 degrees above absolute zero. It's the afterimage of the universe's childhood, frozen in place like a baby picture you'll never update. Behind that fog, no light escapes. The early universe was too dense, too bright, too tangled in plasma. If you want to imagine what lies farther back, you need mathematics, particle accelerators, and a lot of caffeine. It's a sobering thought. There's a built-in limit to what you can ever know. The universe comes with a curtain, a permanent blind spot that no telescope will pierce. Some scientists find this infuriating, others find it comforting. Historians still argue whether the idea of a cosmic edge makes science feel too much like philosophy, but the reality is simple. You live inside a bubble of light, and that bubble is all you'll ever have. And yet, standing at that imaginary horizon in your mind, you don't feel trapped, you feel awe, because even within that curtain, the scale is overwhelming. 2 trillion galaxies, each with billions of stars, planets, and possibilities. Entire dramas of birth and death. Black holes colliding, stars exploding, life may be rising and falling in places you'll never see. It's abundance beyond comprehension, contained within a sphere of visibility that's already more generous than you can absorb. Here's a little joke your sleepy brain conjures. If you could somehow travel to the edge of the observable universe and look back at Earth, you'd see dinosaurs roaming, because their light would just now be arriving. The only problem is, by the time you got there, you'd be too extinct yourself to enjoy the view. The cosmic horizon also raises the most haunting question. What lies beyond it? Is it more of the same, more galaxies, more filaments, more voids? Or does the fabric change, twisting into regions where the physics themselves are different? If inflation really stretched space to near infinity, then beyond your horizon lies an endless continuation, with no edges, no limits. But if space is curved like a sphere, maybe journeying far enough would bring you back to your starting point, like sailing around a globe. The truth hides behind that fog, taunting you with possibilities, and tonight, Lying here, you realize it doesn't matter whether the universe is infinite or finite, curved or flat. What matters is that you have a horizon, that you can measure it, that you can marvel at it, that you can feel its presence like a cosmic shoreline. Beyond it lies mystery. Within it lies everything you've ever known. Both truths hold you gently, like the grass beneath your body and the stars above your face, so you let the thoughts settle. The horizon isn't a wall to fear, it's a soft veil, reminding you that the cosmos has both generosity and restraint. You don't need to see beyond it to feel the immensity of what's inside. The curtain glows faintly in your imagination, a distant light that says, "This is far enough for tonight. Rest here, dream in starlight." The grass beneath you feels cooler now, the air pressing softly on your skin, and your mind begins to tilt with a new kind of question. Not how big the universe is, not how fast it's expanding, but what shape it actually takes. It sounds simple. Is the cosmos flat, curved like a sphere, or bent like a saddle? But the answer isn't just geometry trivia. The shape of the universe decides its fate, determines whether light loops back on itself, and tells you whether infinity is real or just a word humans toss around at bedtime. Think of space like a sheet of paper. If the sheet is flat, parallel lines stay parallel forever, never crossing. If it's curved like a sphere, those lines eventually meet, as if marching around the globe. And if it's curved like a saddle, the lines drift farther apart. Each geometry is allowed by Einstein's equations of general relativity. The universe could, in principle, be any of them. Historians still argue whether Einstein himself leaned toward a closed spherical model because he liked the poetic tidiness of it, or because he suspected nature might prefer finiteness over infinity. The real test came not from philosophy, but from the cosmic microwave background. By measuring the scale of those tiny ripples in the early universe's glow, scientists could check whether space bends light more than expected. The results? As far as we can measure, the universe is astonishingly flat within 0.4% of perfect flatness. That doesn't mean it's infinite, but it does mean that on scales of hundreds of billions of light years, geometry behaves just as your high school math teacher promised. Lines don't sneakily meet up or bow apart, they play nice. Here's a quirky tidbit. In 2001, when the first WMAP results suggested flatness, some headlines ran with, "The universe is shaped like a pancake," technically true in a geometry sense, but pancakes don't stretch in 3 dimensions, and they certainly don't accelerate their edges away at near light speed. Still, the image stuck, proving that even the cosmos isn't safe from breakfast metaphors. Of course, flat is a slippery word. The Earth looks flat when you walk across a field, but step back far enough and the curve reveals itself. The universe might be the same way, flat on the scales we can measure, but curved so subtly that the bend only shows across unimaginable distances. Some theories even suggest space could wrap around itself in exotic topologies, like a torus, donut, or a dodecahedron. Imagine living in a cosmic funhouse where travelling far enough in one direction eventually brings you back to where you started, maybe even seeing your own galaxy from the back. Historians still argue whether the absence of repeating patterns in the microwave background rules this out entirely, or if the universe's wraparound is simply too vast to detect. Lying in the grass, you let yourself picture each possibility. In the spherical version, the cosmos is finite but unbounded, like living on Earth, where you never find an edge but still have a closed surface. In the saddle version, space opens endlessly, curving outward like a roller coaster track, infinite but strangely unstable. And in the flat case, the one most scientists currently favour, the cosmos stretches forever in all directions, uncurved, infinite and steady, though even infinite is a word too large to feel real. Here's your gentle joke for the night. If the universe really is saddle-shaped, then technically you're spending your life lying on a horse you'll never see. Giddy up, stargazer. The shape debate also ties into destiny. A closed spherical universe might one day stop expanding and collapse back inward in a big crunch. An open saddle-shaped one might expand forever, thinning into emptiness. A perfectly flat one hovers between those extremes, with its fate dictated by the dark energy's mysterious push. It's not just geometry, it's prophecy written in the angles of space itself. And yet, for all the measurements, for all the precision of satellites like Planck, you're still left with uncertainty. Flatness to within 0.4% doesn't mean perfectly flat. It could be almost spherical, almost saddle-shaped, or some shape stranger still. Historians still argue whether we'll ever refine our instruments enough to know for sure, or whether this question will remain one of those cosmic riddles that forever teeters on the edge of answerability. So you lie back and let the shapes wash over you. A sphere, a saddle, a plane. Each one is beautiful in its own way. Each one stretches your imagination farther than your breath can reach. You may never know which geometry truly describes the whole, but tonight, beneath the grass and stars, you feel part of the puzzle, curved gently into whatever shape the cosmos has chosen, and maybe that's enough. The night deepens and the stars above you seem to lean closer, almost conspiratorial, as though they know you're about to cross into dangerous territory. Speculation. You've wandered through parallax, redshift, cosmic webs and dark energy, each step grounded in observation. But now your mind drifts toward the multiverse, an idea so strange it feels like science slipping into science fiction. And yet the whispers of it come not from novelists, but from physicists trying to solve puzzles inflation left behind. If inflation truly stretched space faster than light, maybe it didn't stop everywhere at once. Maybe pockets of space kept inflating, bubbling outward into endless regions, each one sealed off from the others by expansion. That picture leads naturally to the idea of bubble universes. You live in one. Somewhere out there, another balloon swells, hosting its own galaxies, its own laws of physics. Perhaps in that bubble, gravity is stronger, or weaker. Perhaps stars never form at all. Perhaps life takes a path unrecognizable to us. Historians still argue whether this leap is a bold extension of inflation theory or a wild detour dressed up in equations. Here's a quirky tidbit. Some multiverse models suggest that in certain bubbles, time itself could flow differently, or not at all. Imagine an entire universe where the concept of before and after simply doesn't exist. For you, lying in the grass tonight, that's almost laughable. How would you ever decide when to eat breakfast? The temptation, of course, is to imagine countless versions of yourself scattered across these other universes. Somewhere, another you chose a different career. Somewhere, another you never discovered your favourite song. Somewhere, another you didn't pause tonight to stare at the stars. This many worlds flavour of multiverse comes from quantum mechanics, where every possible outcome might branch into its own reality. It's a deliciously strange thought that every decision spawns a fork, creating entire new universes with every breath. Scientists argue passionately about whether this is a real description of physics or just a metaphor that got out of hand. And then there are brain world models, spun out of string theory, where our universe is a membrane floating in higher dimensional space. Other membranes drift nearby, invisible to us, yet capable of brushing against ours. Some theorists even suggest that the Big Bang itself might have been the collision of two such brains. Picture universes clapping together like cosmic cymbals, sparking creation in the crash. Historians still argue whether string theory's mathematics deserves to be called science when so little of it can be tested, but the imagery is irresistible. Lying in the grass, you try to picture these other universes. They don't exist out there in space as much as alongside ours, layered in ways your brain isn't built to grasp. It's like living in a two-dimensional sheet of paper and learning that dozens of other sheets float above and below, stacked in a book you can never flip. You can imagine them, but you can never step off your page. Here's a soft joke to lighten the vertigo. If there really are infinite universes, somewhere out there exists one where you actually floss every day and fold your laundry on time. Truly the strangest realities of all. Of course, critics argue the multiverse idea risks making science unfalsifiable. If every possibility exists somewhere, then nothing is ruled out. Where's the predictive power in that? But defenders counter that the multiverse isn't speculation for speculation's sake. It arises naturally from equations we already use to describe inflation and quantum physics. The question isn't whether scientists like it. The question is whether the math leaves any other choice. For you, though, lying beneath the stars, the debate isn't about equations, it's about wonder. It's about imagining your night sky as just one page in a library too vast to catalogue. Maybe those other universes exist, maybe they don't. You'll never touch them, never see them, but thinking about them stretches your imagination like nothing else, forcing you to admit the universe you know might not be the whole story. And the most humbling thought of all, even if the multiverse is real, it doesn't make you less significant. It makes you part of something larger, an infinity of infinities, each one a canvas of possibilities. Tonight you belong to this one, with its stars, its galaxies, its blades of grass beneath your fingers, and that's enough. The night is still, you're breathing soft, but your imagination keeps running ahead, past horizons, past webs, past speculative bubbles of universes. Now you wonder about the tools that let humans push so far, because for most of history, you've had nothing more than eyes and patience, and now you wield machines so powerful they can peer nearly to the beginning of time. The story of measuring the universe's size is also the story of building sharper eyes, telescopes and probes that keep stretching vision farther than the human body could dream. Think of Galileo's little tube of glass, hardly more than a spyglass, and compare it to the James Webb Space Telescope. Webb, a golden hex-eyed machine the size of a tennis court floating a million miles from Earth, shielded from the sun by layers of folded fabric. It's almost comical, like comparing a pocket mirror to the Hubble Ultra Deep Field. But this is what it takes now to keep nudging at the edge of visibility. Webb's infrared gaze slices through dust, capturing galaxies so faint and distant their light has been travelling for more than 13 billion years. To look at its images is to see baby galaxies forming when the universe was only a few 100 million years old. Historians still argue whether Webb's first results in 2022 really showed galaxies that were too massive and too early to fit standard models, or whether those claims were just over-enthusiastic headlines. Here's a quirky tidbit. Webb's mirror had to be folded up origami style to fit into its rocket, then carefully unfolded in space. For weeks, engineers on Earth held their breath as the machine bloomed like a mechanical flower. Had even one hinge stuck, the entire mission would have been a 10 billion paperweight drifting uselessly in orbit. Instead, the unfolding worked perfectly, proving that sometimes humanity's wildest gambles do pay off. But Webb isn't alone. The Hubble Space Telescope, still orbiting after more than 3 decades, gave us the famous Deep Field, a photograph of what looked like empty sky, revealed under long exposure to be packed with thousands of galaxies. Lying in the grass, you imagine that image burned into your eyelids, every speck a galaxy, every smudge a cluster. The shock of it wasn't just scale, but implication. If one tiny patch of blank sky contains thousands of galaxies, then the whole universe must be teeming with them. It was like lifting a pebble and finding an entire city crawling beneath. And the next generation is already on the way. The Vera C. Rubin Observatory in Chile will soon scan the entire sky every few nights, building a dynamic movie of the cosmos. Instead of still photos, you'll watch galaxies collide, supernovae flare, asteroids drift, all in real time. Then there's Euclid, launched in 2023, tasked with mapping billions of galaxies to probe dark energy's influence, and the Nancy Grace Roman Space Telescope. Coming later this decade will take Hubble-like clarity but widen the field 100-fold, capturing cosmic panoramas. It's as though humanity is upgrading from a magnifying glass to a drone-mounted camera, sweeping across the stars with ease. Here's your light-hearted joke. Astronomers name telescopes after famous scientists, but at this rate they'll run out. One day you'll hear about the Carl the Intern Space Telescope, because all the big names were taken. Beyond telescopes, probes push your reach in other ways. The Voyager spacecraft, launched in 1977, are still drifting outward, carrying golden records of Earth's music, greetings, pulse and sounds. They won't map the universe, but they remind you that curiosity doesn't stop at your doorstep. Each probe is a tiny bottle tossed into a galactic ocean whispering, "We were here." Meanwhile, missions closer to home, like Gaia, meticulously charting billions of stars, are transforming the Milky Way from a flat blur into a 3D atlas. Historians still argue whether these missions should be seen as mere data collection or as part of a larger philosophical journey, the same urge that drove Babylonians to track Venus with clay tablets. From reeds and shadows to billion-dollar telescopes, it's the same story told with different tools, humans reaching for scale, for perspective, for context. And lying here tonight, you realise something profound. The universe doesn't reveal itself easily. Each new telescope is not just hardware, but patience, risk, and imagination made metal. Each one stretches your senses, pulling your sight farther and farther toward the edge of time, and the images that return, those faint smudges, those elegant arcs of gravitational lensing, those baby galaxies blinking on the edge of visibility, are proof that your tiny species has dared to measure the immeasurable. So you close your eyes and let the hum of imagined machinery fade into the night. Around you, the grass and insects and air are simple, small, but above, satellites swing silently, telescopes peer endlessly, probes drift into forever. Humanity has built new eyes, sharper than evolution ever gave you, and through them you're learning the true size of home. The stars above you are steady, serene, but your mind can't help peering ahead, not just to where telescopes reach, but to where time itself is headed. You've measured the size of the observable universe, traced its scaffolding, even toyed with the notion of multiverses. Now comes the haunting question: what will become of all this? The fate of the cosmos is written not in mythology, but in physics, and depending on which numbers win, the ending could be a slow sigh, a violent tear, or a strange rebirth. The simplest scenario is the so-called heat death, or big freeze. Imagine the universe continuing to expand under the steady push of dark energy. Galaxies drift farther and farther apart, their light redshifting until it fades into invisibility. Stars burn out one by one, leaving behind only black dwarfs, neutron stars, and black holes. Over unimaginable timescales, trillions upon trillions of years, those too decay, evaporating via Hawking radiation. What's left is a universe of thin, cold particles and energy, stretched into silence. No fireworks, no bang, just a long dimming, like the embers of a campfire cooling under ash. Historians still argue whether heat death is a misleading term, since it's actually the absence of usable heat, but either way it's the ultimate cosmic yawn. Then there's the more dramatic option, the Big Rip. If dark energy's repulsive force isn't constant but grows stronger over time, the expansion could accelerate without limit. First galaxies would fly apart, then stars would lose their grip on planets, then atoms themselves would be torn as the very fabric of space stretches past breaking. In this version, the end of the universe isn't quiet, it's shredding, as if reality itself were caught in a cosmic blender. Cheerful bedtime thought, isn't it? Here's your joke to soften it. If the Big Rip happens, at least you'll never have to fold laundry again. A third possibility is the Big Crunch. If dark energy weakens or reverses, gravity could eventually slow the expansion, halt it, and then pull everything back inward. Galaxies would collide more often. Stars would burn hotter. And in the final collapse, the universe would shrink into a dense fireball, back to something like its earliest state. Out of that chaos might spring another Big Bang, and perhaps the cycle repeats forever. Some cosmologists like the elegance of this loop, others dismiss it as too speculative. Historians still argue whether ancient Hindu and Buddhist cosmologies, which spoke of endless cycles of creation and destruction, were eerily close to this scientific picture, or whether the similarity is just poetic coincidence. And then, of course, there's the wildcard option, something no one has imagined yet. Maybe new physics will reveal a hidden mechanism, a twist in the story that neither heat death, nor Big Rip nor Crunch predicted. The future, after all, has a way of outsmarting human expectations. Lying in the grass tonight, you let each fate drift through your mind like dream scenarios. In the heat death, the stars above you flicker out one by one until the sky is black forever. In the Big Rip, the constellations unravel, then atoms, then even the molecules in your body. In the Big Crunch, the stars blaze brighter and hotter until everything folds into a final firestorm. Each version is terrifying in scale, but strangely, none of them make you afraid, because all of them are so far in the future that even the concept of future struggles to hold its shape. The timescales are longer than Earth's lifespan, longer than the lifetime of stars, longer than your imagination can stretch. Here's a quirky tidbit. According to some estimates, the first black dwarf supernova, the explosion of a star so dead and cold it's nearly invisible, won't occur until 10 or 1100 years from now. That's a number so large it makes 93 billion light-years look cozy by comparison. If the universe had a calendar, that date would be written in invisible ink. So what's the point of pondering all this if you'll never see it? Because imagining the end helps you savor the present. Right now, galaxies still sparkle, stars still burn, planets still cradle life. You live in a rare, vibrant epoch when the night sky is ablaze with light, when telescopes can still trace the cosmic web, when the microwave background still hums with its ancient glow. Future beings, if any exist, may find themselves in a darker, lonelier universe. You, by pure luck of timing, get the fireworks show, And so you let your breath match the steady pulse of the stars. The universe has its fates, its prophecies, its possible endings, but none of them touch you tonight. You are here, in this sliver of time beneath a sky that still sings. Whatever comes trillions of years from now, tonight is filled with starlight, and that's more than enough. The crickets hum around you, the stars scatter above you, and your thoughts shift gently from science into the echoes it leaves in culture. Because measuring the size of the universe isn't just physics, it's philosophy, religion, art, and even humour. Every culture has wrestled with infinity, with the vastness overhead, long before astronomers drew parallax diagrams or pointed telescopes skyward, and in some ways, the cultural responses are even more fascinating than the measurements. Think back to the Babylonians and Greeks, who saw the sky as a dome, finite and protective. Compare that to medieval Christian cosmology, where heaven was placed just beyond the firmament, the stars acting as windows to divine realms. Or the Hindu and Buddhist traditions, where the cosmos cycles endlessly, worlds arising and dissolving without beginning or end. Historians still argue whether those cyclical visions bear any resemblance to modern Big Crunch and Big Bang scenarios, or whether it's simply humanity's natural instinct to imagine beginnings and endings repeating. Here's a quirky tidbit. The Norse imagined the universe held together by Yggdrasil, a cosmic ash tree whose branches stretched across realms. It's oddly similar to the modern idea of the cosmic web, with galaxies hanging like fruit. Of course, the Norse also believed a squirrel named Ratatoska carried insults between an eagle and a dragon, living on that tree, not exactly in the Planck satellite's data release, but still a poetic precursor to cosmic connectivity. Art too has always reached for a scale. Medieval manuscripts painted concentric circles of heaven and stars. Renaissance artists tucked cosmic spheres into altarpieces. In the 20th century, painters like Salvador Dali twisted galaxies into surreal swirls, while science fiction illustrators flooded books and pulp magazines with starfields. Even today, every time you see a blockbuster movie with sweeping shots of galaxies, you're witnessing the cultural digestion of cosmic immensity. It's not just data, it's inspiration. And religion? The universe's size has always been a touchpoint for faith. For some, vastness proves divine craftsmanship. The bigger the stage, the greater the playwright. For others, it raises uncomfortable questions. If the universe is so immense, why this tiny planet? Why this fragile species? Historians still argue whether Copernicus's demotion of Earth from the cosmic centre shook religious thought as deeply as later scientific revolutions. But there's no doubt each leap in size has forced new reckonings. Lying in the grass, you realise even everyday language borrows from infinity. We call someone's love endless, our patience astronomical, our debt cosmic. Infinity slips into poetry, into lullabies, into casual exaggerations. Humans seem to need the sky as metaphor, as if measuring the universe also measures the human heart. Here's your soft joke for the night. People once feared infinity would break their theology, yet today they slap infinite on pizza buffets. Humanity's relationship with the cosmos has always had a sense of humour. And then there's music. From Holst's The Planets to space-age jazz to ambient tracks built from NASA recordings of plasma waves, composers keep trying to capture the feeling of immensity. Some cultures still sing seasonal songs tied to constellations, echoes of the same sky-gazing impulse that once guided farmers. In this sense, the universe's size isn't just measured in light years, it's measured in symphonies, paintings, metaphors, myths. Historians still argue whether science has stripped away the wonder of the heavens or deepened it. Some say measuring distances and crunching numbers makes the cosmos cold and mechanical. Others argue the opposite, that knowing galaxies are billions of light years away makes them more magical. You lying here under the stars can feel the answer. The numbers don't erase the awe, they expand it. 93 billion light years isn't a demotion, it's a lullaby sung louder than you expected, so you let your eyes close halfway. The grass pressing gently at your back, and you imagine all the humans who've ever stared upward. Poets, monks, painters, musicians, philosophers. Each one trying to capture infinity in their own language, each one contributing another layer to the chorus. The universe may be too vast to hold in your mind, but it fits perfectly in the stories people tell, and tonight, those stories keep you warm. The grass beneath you is damp with dew now, the air cooler, and your thoughts feel heavy, ready to settle. You've drifted across history, science, speculation, and myth, and now the journey returns to something simpler. You, lying out under the night sky, letting the infinite shrink into something personal and calm. The universe is immeasurable, 93 billion light-years observable and perhaps infinite beyond. But tonight it's also just the stars above your head, glimmering as if lit for you alone. You imagine walking slowly across a quiet field, shoes brushing against tall weeds, each step pulling you deeper into the hush of night. The sky arches like a dome stitched with constellations, Orion, the Dipper, Cassiopeia, patterns your ancestors named to keep from feeling lost. Their shapes are stories, anchors against infinity. You can almost hear the echo of their voices, pointing upward, telling children tales of hunters, queens and bears, not because the stars truly form those figures, but because naming them made the dark feel friendlier. The observable universe may span 93 billion light-years, but your eyes never need to travel that far. They need only a patch of sky to remind you that you belong to something larger. Historians still argue whether our instinct to personify the heavens, seeing gods, myths, animals, was just survival psychology or the seed of science itself. Either way, the impulse is the same as yours tonight, to find meaning in the glitter overhead. Here's a quirky tidbit to keep tucked in your mind. In 1910, when the Voyager 1 spacecraft looked back at Earth from 3.7 billion miles away, it captured the famous pale blue dot photograph. Our entire planet was a speck, smaller than a pixel, floating in a shaft of sunlight. Carl Sagan wrote that all of human history has happened on that mote of dust. And yet, even from that tiny vantage point, the universe felt intimate, as though perspective itself was a form of comfort. So you'll imagine yourself shrinking the universe down. Galaxies become fireflies. Clusters become lanterns. The cosmic web becomes strands of spider silk across your fingertips. Suddenly, infinity isn't overwhelming, it's gentle. It rocks you like waves on a shore, its immensity softened by the fact that you'll never have to hold it all. You don't need to. You only need to notice it exists. Here's your final sleepy joke. If the universe really is infinite, then technically somewhere out there exists a galaxy where every star is arranged in the shape of a giant smiley face. Take comfort. It's proof that even infinity has a sense of humour. The air is cool, the stars steady, and your body relaxes into the grass. The universe is larger than numbers, stranger than theories, richer than myths, but right now is also quiet, kind and present. The same sky seen by Babylonian priests, by Galileo, by Vera Rubin, by you. 93 billion light-years observable, perhaps infinite beyond. And tonight, all of it condenses into a single truth. You are here, safe, breathing, small but not insignificant, part of a cosmos vast enough to cradle you forever. And with that thought, you let your eyes close.